Welcome to The Explainer. Today, we're going to get into a really fascinating and, let's be honest, pretty unconventional theory about something we see every single day: color. And it all kicks off with a question that seems simple, but when you really dig into it, well, it just doesn't seem to make any sense. Okay, so let's get right into the puzzle that started this whole thing for the author of our source material, a painter by the name of Mathis. We're taught that if you mix red light and green light, you get a bright, clear yellow. Okay, seems straightforward enough. But if you're an artist who works with color all day, that answer is just wrong. You see, as a painter, he knows from experience that when you mix red and green paint, you get a murky, muddy gray. It's intuitive. They're opposites on the color wheel that cancel each other out. And yet, when you mix beams of pure light, you get this vibrant, pure yellow. This is the whole basis of what we call additive color. To an artist's eye, this is just deeply weird. When you look at that yellow light, you don't see any of the red or green that supposedly made it. It just feels wrong. And it's this exact contradiction that sparked a complete re-examination of how we think about color itself. So how does this theory even begin to solve this puzzle? Well, it starts by making a pretty bold claim that the primary colors of light, red, green, and blue, aren't actually primary at all. They're already mixtures themselves. According to this idea, that beam of red light we see is actually a combination of yellow light and magenta light. And following that same logic, a beam of green light isn't just green, it's a mix of yellow and cyan. Okay, so if those are the real ingredients, what happens when we mix them together? Well, this leads us to a brand new mechanism that the author came up with. He calls it the knockout effect. So here's how it's supposed to work. When you overlap those beams, the theory says that the magenta part from the red light and the cyan part from the green light are direct opposites. So they just knock each other out. They cancel, they disappear. And what's left? You've got the yellow from the red light and the yellow from the green light. And they combine to create one strong, pure yellow beam. But wait a second. For any of that to work, magenta and cyan have to be true opposites. And that brings us to the absolute central clue in this entire investigation, the very strange color magenta. Magenta is, well, it's just plain weird. It doesn't show up in the visible light spectrum. You will not find it in a rainbow, no matter how hard to look. That's why it's often called a non-spectral color. It kind of shouldn't exist. So, what's the standard explanation? Well, it's that our brains literally just invent magenta to fill in a perceptual gap. The author of this theory thinks that is completely unsatisfying. He actually calls the idea daffy. He says there has to be a real physical reason for it. Right, so if our brain isn't just making magenta up out of thin air, what is it? This question leads to the absolute core of this theory, and a totally new kind of particle. The theory introduces something called the antiphoton. Now, this isn't some exotic antimatter from science fiction. It's actually much simpler. Think of it like a spinning top. The theory suggests that some photons, particles of light, spin one way, say clockwise, while others, the antiphotons, spin the exact opposite way, counterclockwise. And this gives us a whole new way to categorize color. You've got your standard photonic colors, the ones that spin one way, like green and cyan, and then you have your antiphotonic colors like magenta that are physically spinning the other way. And this is the physics behind that knockout effect we were just talking about. When a photonic color, like cyan, comes into contact with its antiphotonic opposite, magenta, their opposing spins literally clash. As the author puts it, they catch like little gears and poof, they neutralize each other. Okay, so this is a really cool idea, right? A totally different way of seeing color. But is there any physical evidence for it? Well, the author points to a really simple experiment that you could do right now with a prism and the very screen you're looking at. So if you happen to have a simple prism and you look at the black text on your white screen through it, you're going to see something very, very specific happen. First, the black text itself will appear to turn magenta, but then you'll also see two ghosts of that text. There's a yellow ghost that's bent sharply upward and a cyan ghost that's bent slightly downward. And here's the kicker. The magenta itself stays put. It doesn't bend. According to the theory, this is the smoking gun. The fact that yellow and cyan bend in opposite directions is presented as direct physical proof that they have opposite properties, which is exactly what you would expect to see from particles that have opposite spins. Now, if this theory actually holds water, the implications are, well, they're huge. It would mean we have to completely rewrite color theory from the ground up. It would mean that color isn't just about wavelength, but also about the direction that light is spinning. And get this, that implies that our eyes are far more sophisticated than we ever thought. They're not just detecting frequencies, they're detecting the spin of photons. It means magenta isn't some trick of the mind, it's a real physical thing. And that really leaves us with a final, pretty provocative thought. If you challenge something as fundamental as color, it makes you ask, how much more of our reality, of the basic mechanics of the world we see every day, might be hidden from us, right there in plain sight?